Our next speaker is Matthew Abrahamson from the Jet Propulsion Laboratory. He's going to be talking about a payload that's going up actually on the next SpaceX flight, right? SpaceX 3?
Right, SpaceX 3.
Optical payload for Lasercomm science. This is basically a demonstration payload, I would call it. And he's going to show you what they're up to, and then he's got a cool video too.
Okay, thanks Mary Beth, and thanks everybody for having me here. I'm here from the OPALS payload at the Jet Propulsion Laboratory. And what we're going to do is we're going to sit on ELC-1 and demonstrate an optical link space to ground using optical communications. And this project started off as almost a training project at JPL for early career hires. So everybody who's worked on this project is basically 20-somethings, and we've been working on this for about 4 years. We just got to the point of shipping to Kennedy Space Center 2 weeks ago. We're down there doing our launch integrations now, and we're planning to go up on SpaceX 3 this December. And we're all very excited about it. So what I'd like to talk to you about today is some of our pointing strategy of how we're pointing an external payload down at the ground. And I think this might have applications to a lot of external payloads for trying to do the same thing for either observation or transmission down to the ground. So why is laser communications an important technology for us? Well, at JPL, we're in the remote sensing business. We're out there in the deep space arena. We're trying to get data back to the ground, and this data is gold to us. And laser communications is a potential technology that could potentially increase data rates 10 to 100 times what they are today. Currently from Mars and deep space, we're getting back data rates on the order of kilobits per second and hundreds of kilobits per second. Optical communications has a potential to go up to megabits per second and gigabits per second. So instead of waiting 10 minutes to get a single image down from Mars, you could have streaming HD video back from Mars. And so that makes it a very appealing technology for JPL to investigate. Now, what is OPALS doing? Well, OPALS is the first step. In this technology, you take baby steps. We're going to be JPL's first space-based platform for demonstrating this technology. And that's what it is. It's a technology demonstration. It's a chance to get our feet wet over a year, practicing optical links and seeing some of the characteristics of how you close this optical link. We're really not innovating when it comes to data rate. We're going to be starting around 30 to 50 megabits per second. But the real innovation of this payload is the cost, and that's what the ISS has allowed us to do, is to bring the cost down through not being constrained from mass or power, and using a lot of COTS parts for this technology demo. So what will OPALS do? Well, the real power of OPALS is to do this demonstration and record the statistics of how well we can close an optical link over time. So we get a lot of information about the atmospheric turbulence and how that is affecting our optical link. We can validate a lot of our optical pointing budget. Right now, a lot of the pointing budget assumptions are just on paper, and until we test those out, we don't really have a good idea of how often our signal is going to fade, how much power we can really get to the ground. What OPALS allows us to do is really play around with it as a laboratory test bed and see how our optical link changes over different geometries, different ranges, different ground stations, and different atmospheric effects that are going on in the atmosphere. And one of the major assets and facets of optical communications is pointing. We need to point very precisely towards the ground in order to get enough power on the receiver. And so I've circled over on the right-hand side the pointing that we're looking for. We're assuming a pointing bias of about 150 microradians, one segment, about a jitter while we're tracking the ground station about 125 microradians, one segment. So it's a fairly tight pointing requirement. So what I want to talk about today is how we're trying to meet that pointing requirement and our results so far in that endeavor. Here's our flight system as it looks today. What you see here is two main components of the flight system. There's a sealed container, that's that big tank on the right side over there, and that's housing all of our avionics that are commercial off-the-shelf grade electronics. A lot of those are just National Instruments parts that you can buy and use in the lab, and we've just stuck them in a tank and sealed it and pressurized it to 1 atmosphere, and that really allows us to bring the cost down. The second object you see there is the 2-axis gimbal upon which there's an optical head mounted, and that's our optical transceiver pointed to the ground. So we have the capability to actuate in an azimuth direction and an elevation direction as we track a ground station on the ground. One thing to point out is when you go to the station and say you need to point very accurately, they say, well, you shouldn't rely on our GPS or our star trackers. We really recommend that you get your own star tracker and GPS receiver, and we just didn't have the cost for that. In fact, we even have the money to have motor encoders. So in fact, our motors on our gimbal are just dead reckoning. We're just counting the steps that we command. And I'll talk a little bit about how we deal with that and how we calibrate this gimbal in order to get around that cost constraint. So how are we oriented on the ISS? We're going to go on ELC1. That's over on the port side. And this is looking at the ISS as the ISS is coming towards you. So we're kind of pointed inwards towards the center of the ISS. And we have a field of view that's about 110 degrees along track of the ISS by about 40 degrees cross track. And I'll talk a little bit about why we're restricted to those pointing angles. But you can imagine when you have a laser beam up on the station, people are very concerned about you hitting any part of the station or the astronauts or visiting vehicles. And how are we going to go through and transfer this video? So here's our concept of operations. Effectively, we have a ground station. This is in California on a mountain called Cape Mountain, about 7,500 feet above sea level. We'll send predictions over the Optical, so we'll start tracking this pass over the ISS as it's expected to go overhead during a pass. Once the ISS passes over the horizon, we preload some predictions up on the flight system that'll look around and start to look down for that ground station. From the ground station, we're emitting a laser beacon up to the station. And we have a camera up there. Once that camera locks onto that beacon, we have a feedback control system that effectively gives us that pointing we need down 125 microradians. And that'll track all the way through the tracking pass, which can vary anywhere from 30 seconds to as long as 3 minutes. And during that time, we'll be modulating a video over this laser beam coming down to the receiver here. And on the ground, we'll be decoding that video and replaying it back in real time and seeing what our bit error rate is as we get down to the ground. So how is our pointing restricted up on the station? We have this field of regard that we've defined, and we had to work a lot with JSC Safety over at Johnson to define this. And in fact, we've designed something so that we can never irradiate any part of the station, any part of the solar array envelope that's going through, or any of the visiting vehicles that might happen to be up on station. So what that allows us to do is almost any time we want to operate, we'll be able to schedule a command window. The only times we can't is if there's a visiting vehicle that is phasing to the ISS, if there's an EVR that will violate this field of regard, or if there's an EVA activity going on. So that really gives us a lot of opportunity to work around those constraints. And this is really an example of how mission success has been at odds with mission safety. Mission safety is trying to restrict this to a smaller field of regard, and as we bring that field of regard down, we get shorter pass durations and shorter frequencies. So as you can see here, this is our field of regard extended onto the ground track. And so we have our long axis, luckily, is a long track. So this is our pass duration, really, and then the cross track is our pass frequency. So right now, with this analysis, we think that we can probably operate once every 2 or 3 days. So the pass frequency is not as ideal as we'd like it, but we do get a pretty good pass duration of about 3 minutes at maximum. So here's the pointing architecture that we're trying to deal with. We're getting this bidirectional pointing with the Optical and the OPALS payload. We have the Optical to OPALS pointing, and that's based on open loop pointing based on propagated state vectors, and I'll talk about that a little bit later. But the accuracy we're trying to get there is 500 microradians, and that's to get the receiver pointing towards the transmitted video coming down. On the other side, we have this concept called blind pointing. It's effectively open loop pointing up on the ISS. We're going to send up some predicts that will search around and look for this beacon. We can tolerate about 1 degree of prediction error. Once it locks onto that first centroid on the camera, it goes to the PI control loop system, and at that point, that's when you get down to 125 microradian requirement. So let's talk about the ground to space pointing and what we've done so far on that end. So how does the ISS look when you're viewing it from Optical? Well, over this pass, given our field of regard, we can start to see it in view when it's about 850 kilometers range from the ground station. It comes down, and after about 1.5 minutes, it's down to minimum range directly overhead. That's about 410 kilometers. And then on the way out, we can get it out till it's about 600 kilometers. And so the ground station, the pointing we have to provide over there is an azimuth and elevation relative to the local topography. That's usually looking northwest up towards San Francisco as it comes overhead, turning around and looking as it passes down towards Arizona overhead the ground station. And so how do we get these predictions over to the Optical? Well, we're going to propagate. So what we do is we pull down a state vector from the broadcast stream that's coming from the station, and we feed it into our JPL navigation tools and propagate that forward using a variety of models, gravity, solar pressure, atmospheric drag. Propagate that trajectory forward to get a prediction on the trajectory, and then we convert that to the local azimuth and elevation profiles I showed you on the previous page. And what we're looking at there is, again, to get it within this 500 microradian scope, and if you're at 400 kilometers, that computes to about plus or minus 100 meters trajectory. So how do we do? Well, this is how we assess what we're doing. So I'll pull down a state vector from the broadcast data, that's this R0V0, propagate it forward. I'll send that over to the station operators, they'll track the ISS. And after we're done, then I'll get an entire playback of all the GPS states from the GPS receiver up forward. I'll do the differencing and see how well we did with the trajectory. So here's one pass we did, and this is where we took the initial state vector. We propagated forward about 30 or 40 minutes. And the error only rose to about 35 to 40 meters, so we're doing about a factor of 2 better than we need to. So this is really good, but we wanted to encourage ourselves and do this multiple times. So we did it again on April 3rd. And again, miraculously, we're still getting between 15 and 30 meters trajectory error. How does that compute the angular error? Well, if you do the conversion over to azimuth and elevation, we're still under 100 microradians, so we're doing pretty well on pointing. Now here's a picture you probably want to see. This is how we see it from the ground. This is a picture as the ISS is approaching the ground station. This is a sunlit pass, so this is at 5:30 in the morning California time. And we get a pretty nice picture here with scopes. You can see ELC1 is up here. This will be located, so we'll be seeing the laser coming down from this ELC1 location here. On the other side, we can actually see the aft side. So it's really cool when you see the video. You can see the ISS actually turn. You see the underside, and then you see the back side of the ISS. And I have a video here. If it works. Let's see, how do I get back to the desktop?
Minimize your...
I'll just minimize it.
Yeah.
So this is a tracking pass from April 3rd that we performed. Okay, so it's a long pass. It's about 6 minutes long, but this is about close to the approach. So you can almost see as the beta angle changes, you can start to make out a little more of the structure of the ISS. But this is a really great validation for us because we were never sure if we could get enough accuracy to track this open loop. There's no active tracking going on here. This is all predictions.
Question.
Yep.
Is that natural seeing or is that with adaptive optics?
Say again?
Is that natural seeing or is it...
This is what you would see through the scope. Yes. And you see a little bit of jitter, but it's really not bad. And the idea is keeping in the center of the scope, we can get enough power from our transmit beam to be able to reconstruct this video on the ground. Okay, so that's the ground to space problem. Now the space to ground pointing, the important one, because this is where we're getting our video down to the ground. So how does the optical look if you're looking from ELC1 on the ISS? Well, in our gimbal frame, you're going to start off looking ahead. So we'll be out over San Francisco somewhere, looking up about 60 degrees. And you start off with an angular rate of about 0.2 degrees per second. But then as you get over the ground station, you're going to accelerate up to about 1.2 degrees per second to go overhead. And then decelerate again back to 0.4 degrees per second. And these vary over time. There could be some low passes that are easier to track. Some go up to 80 degrees. I think the one that I just showed you was about a 70-degree pass for the ground station. How do we get the pointing set? So I mentioned before we don't have any motor encoders, so we have to effectively dead reckon this thing. What we do have is we have these limit switches at the end of our field of regard on our gimbal. That allows us, that's there for laser safety. We can also have dual use for gimbal calibration. So prior to every pass, we effectively drive the gimbal to each one of these limits and measure when we get that switch, when that switch is actuated. And when that's actuated, we reset the gimbal angle. And from the calibration, once we do a demonstration, we're only seeing like a 1/10 of a degree maximum loss of calibration. So these motors do pretty good once you calibrate them. And this really allows us to save a lot of cost on trying to point to the ground. Once we get calibrated, then it's time to go and search for that laser beacon that's being shined up at the ISS. And what we do is we provide this thing called the blind pointing table. And for the blind pointing table, we need not only trajectory information, but also attitude information. So I mentioned how we get the trajectory model propagated forward, we get that prediction. So how do we get a prediction of the attitude? Well, we can take a batch of data, and relative to local vertical, local horizontal, the attitude is relatively stable. They have a pretty good controller up there. So if you take a batch of this data, do a fast Fourier transfer of it to get the maximum peak of what the period of that oscillation is, and then project that forward to get the attitude we're expected to be at when we're flying overhead. And once you combine those two, we can put that into a blind pointing table. And we have several different flavors of blind pointing table. We have our nominal pointing profile, and that'll put our camera along where we expect the ground station to be. But if we encounter any other errors, or if there's extra reflection between the ELC and the main node, which is where the attitude information comes from, we can also do searches. So we've added some blind pointing tables that have a spiral search, where we'll start with the nominal profile, but from that, relative to that, we'll do a little spiral search around it. We can also do an azimuth sweep relative to that, or an elevation sweep. And the idea is just to get that beacon. Once we get a couple of centroids, and the camera is confident that it's getting the right signal from the ground, it will lock on and get down to the 125 microradians. So what happens at that point? At that point, we get a centroid on our camera. We pull that to the center of the camera using a PI control loop. And we've been able to test this in the laboratory using a rotary stage. We mount this gimbal on a rotary stage, rotate it with the angular velocity of the ISS as it goes over the ground station, and watch as our control loop does its performance. And you can see here, here's where it's compensated. This is the commanded velocity by the control loop. That's basically the ISS profile. It's starting off at about 0.4 degrees per second, ramping up to 1.2, and then back down to about 0.8 degrees per second. And we're showing really good performance at this point. We're staying within a pixel of our camera tracking, and that's going to give us our 125 microradians 1 sigma. So we're pretty confident that we're going to be good on orbit. There's one last thing. You might wonder, well, okay, you got your camera, you take your laser beam, put it in the center, but how do you know that that laser beam that's going down to the ground is aligned with that camera? Well, we can do some calibration on the ground and see how well it's aligned, but it may settle from launch, and it might move around due to the thermal fluctuations on orbit. So we have this in-flight calibration plan where we'll effectively, while we're in closed loop, we can do a relative motion relative to that closed loop. So we just move the target around. We move it up and down in a raster search pattern. And based on that, we can see how the misalignment changes between repetitive raster search patterns. And so what this is demonstrating, this is in the laboratory, every time we pass over that sweet spot of when the laser is right on the receiver, on the ground you can measure a peak in that laser beam. And so basic raster search will report on the ground, and by looking at the difference between those peaks, we can effectively measure any misalignments in the azimuth and elevation between our receiver and our transmitter. So that's all the pointing. I also want to mention that OPALS is really, aside from being an optical communications testbed and demo, we're also kind of trailblazing in a lot of areas. We are the first JPL spaceborne lasercomm instrument. JPL's done a lot of ground space comm. They've also done a lot of receive space comm, but we never put a payload up in orbit and transmit everything. So this is really great capability for the guys at JPL. It's also the first U.S. lasercomm terminal on the ISS. There is a Russian lasercomm terminal, and we are looking to collaborate with them possibly, but it's nice for us to have one up there as well. It's the first JPL designed to use forced convection. Typically at JPL, for all of our missions, we use conduction. And so to get in this realm of using COTS hardware, you really have to move over to convection for one. It's the first JPL-built unpressurized payload going on the outside. We've sent a couple up on the inside, but this is really new business we're looking to get into. We're going to be the first JPL cargo to fly on SpaceX. Like I said, we're on SpaceX 3 in December. And we're the first FRAM-based cargo to fly on SpaceX, and we're going to fly in the trunk, and so we'll be there with HDEV, which is also going up with us. This will be the first flight of the new Dragon, which is version 1.1. That'll be very exciting to see in December. And along with that, we'll be the first FRAM-based cargo to go through this extraction technique. So we're going to work with the robo guys over at JSC to really get this down and make sure we got the transfer from our cargo to our ELC location all set. So we're very excited to go forward, and just want to mention all the team members. We've gone through quite a journey here, all of us together, and we're really excited to finally get in orbit and do some demonstrations. That's it.
Do we have any questions?
When you first illuminate the ground from the station, single power level? In other words, do you hunt around and lock on using low power and then switch to high power?
No, it's all going to be high power. Yep, we ramp all the way up. We have a 2.5 watt laser. It's about 2 watts at the aperture.
Okay.
And that's what will be probably 10 minutes before our demonstration.
Okay.
Yeah.
What kind of beam diameter would you envision for deep space communication?
Oh, that's a good question. I'm not sure. I'm not the optical comm expert. But I did hear that they were looking between Mars and Earth about 250 megabits per second is the data rate they could look to get back along that link. Now, I should mention, what this can really help us demonstrate from LEO down to the ground is a concept of perhaps on Mars 2020 putting a receiver on the ground and having that asset between Odyssey or something in orbit and something on the ground, doing that sort of technology demonstration. And so there's been some talk about, if we do get an extended mission for OPALS, trying to transmit down to a 2020-like receiver on the ground.
Just to clarify, you said you have just a few minutes per pass for comm. I'm used to thinking, as long as 15, 20 minutes that you might have for a pass for any normal comm. Can you just to clarify? Is that just the ISS restrictions, or is there any other practical issues, atmospheric or whatever, that's preventing you from trying more than that?
Yeah, we're limited to about 3 minutes because of our field of regard that I mentioned before. Now, if you eliminate that, pass over Optical, I think, is about 10 minutes long. So we're cutting it more than in half because we can't point in certain areas. But if you didn't have the restriction, you just had a spacecraft up there, you might be able to double the duration.
You got to pay for software.
Yes, we do. That's very important. It's a little bit of a lengthy process, but we'd eventually like to do that. And like I said, we're starting out at 50 megabits per second, but the hardware can go up to 200 megabits per second. So that's where we'd like to be eventually.
Long term, are you looking more to a network-based architecture where you've got geosynchronous satellites that are communicating with the ground and doing space-to-space communication between them?
Yes, not for OPALS. We're pretty much restricted to point towards the ground based on our field of regard, but that's the idea. Is this is a demonstrator for future space-to-space comm as well as space-to-ground and space-to-deep space. Yeah.
So you mentioned that it's open loop, no feedback. But you mean with regard to what's that sort of state, or when you lock on, after you lock on ground laser?
That's closed loop. Once we lock onto the laser, we're closed loop with the laser beam.
Okay.
The gimbal, the motors are always open loop. We're just counting the steps. The only feedback we ever get is we get the switch at the end of the field regard. And it's big, good enough for us. It's an important point that we did not need to buy motor encoders. Significant cost savings by eliminating those.
You mentioned you use fast Fourier Transform to predict of the oscillation within the control station. What kind of period of oscillation are you seeing, and how much of a factor is that in your
Yeah, it's only about once per rev, so once per 90 seconds, one per 90 minutes. I think I showed here. Okay, so I showed like several hours here of oscillation, but if you limit it to just our pass over Optical, you see the trajectory is changing quite a bit. The attitude is only changing, a couple hundredths of a degree, so it's almost fixed. Our control loop is going to compensate for this very easily.
What's the impact of weather systems, clouds, and things like that on your performance?
That's very important. So a lot of that is what we want to learn, but obviously when there's cloud cover, we can't transmit through cloud cover. Now if there's atmospheric disturbance, there's just some wispy cirrus clouds, we might just get some fading. That's really what we want to learn from this mission, is to get that data. Because like I mentioned, all of our assumptions are just on paper right now. Once we get a chance to test this out and send it to the atmosphere, we can see what it really takes to close an optical link and see how often this will fade.
And this works both day and night?
That's right.
Is there a difference in signal and noise between the two?
There's definitely a difference in our background that we'll see in our camera during the day. And so our baseline is to start at night. Okay, we'll start demonstrating at night. If we're successful there, we'll try to move into the day and see if we can do some interesting image processing techniques to get rid of that background.
At your attitude, do you know how much jitter you have, though, between where their star trackers are on station and where you're located?
So yes, we built that, and I guess you're saying, you get this data, and this is not at your ELC.
Right.
That's correct. Yeah, so that's part of this big pointing budget we came up with, and so we're assuming something like 3 degrees per axis for flexing of the ISS. We're assuming certain amounts for misalignment of the FRAM to the ISS, misalignment of our gimbal to the FRAM. So once it gets down to it, we're just budgeting 1 degree for this, so that's kind of a sub-allocation of the total overall pointing budget.
Do you think once you try to, you're not going to close your loop, you're just going to search? And so your search has to take out the jitter then, that's out there at the LC?
Yeah, we don't expect it to be high frequency jitter. We do have some platform disturbance characteristics, and there's not really a lot of high frequency stuff. It's low frequency. You know, based on the bandwidth of our control loop, it looks like we can compensate for most of the things we'll see on the ELC. A lot is low frequency. Yeah.
Do you program into it prevention of pointing at the sun or something like that, or is that just impossible because of the angular configuration?
That's a good question. Actually, that just came up. So we usually cannot point at the sun except for when we're pointing ahead.
Yes.
That 75-degree point ahead.
Mm-hmm.
And so we're going to look into that. There's an office at Johnson that can provide us those opportunities when we'll look at the sun. At first, we might just avoid those cases where we're going to see the sun on orbit. So we probably would not do it around dusk or dawn. I guess that would probably happen at dusk or dawn, I believe. Yeah. So we probably avoid those at first, and if we do feel a need to actually explore that, then we might look at ways of avoiding that sunlight. Anything else? Okay, thank you very much.